In the previous episode, we installed this custom-made crankshaft pulley on our 719cc supercharged Kubota diesel-powered Honda Insight. This pulley, along with the smaller pulley, are actually the drive pulleys for the AMR500 supercharger that we're using on this little diesel engine. After running the engine with these pulleys, we discovered the supercharger was developing a whopping 12 psi of boost at full throttle and 10 psi of boost when the car was at cruising speed. Not too shabby. You see, our supercharger is now developing instantaneous boost, and while it isn't massive, it's enough boost to make a difference. Anyway, I reckon all we need now is a way to control the boost, because we really don't need 10 psi boost at idle. Keep in mind, this is a very small engine, and we're trying to keep things both simple and cheap. That's why we installed a simple 12-volt solenoid valve to effectively turn the boost on and off. You see, this valve is normally open and it vents the boost until it's triggered. Right now, this solenoid valve is controlled by this handheld switch to momentarily turn the boost on and off, and for longer times, we wired in another switch. So the handheld switches were just a temporary way to control the boost so we could do some testing. Today, we're going to build a system that will automatically trigger the boost solenoid to close when the accelerator pedal is depressed a certain distance. Now, there are about 1 million ways to make a gizmo that attaches to the accelerator to control the solenoid, but each has its pros and cons. What we want is something that's easy to access, easily adjustable, and is both durable and reliable. So we came up with this. Right now this is just a pile of parts, but not for long. We'll get back to this stuff in a minute. So the first and most important part of this supercharger boost venting system is the switch needs to be easily accessible. And what I mean by that is, I don't want to crawl under the dashboard to fiddle with stuff. So we'll be mounting this switch system to this heavy-duty steel support bracket in the engine bay. As it turns out, this is the perfect spot to put a complex gizmo and have easy access to it. So this pile of parts is what we're going to be using to trigger the boost control solenoid. Some of these parts are made from 3D printed high temperature medium strength ASA plastic, and other parts are made from chunks of 6061 aluminum, like for instance this guy. Now, the reason this part is made from aluminum is because this is a throttle cable bridge thingy, and it's hard to say if plastic would have enough strength to work in this application. Actually, this switch system is complex for what it does, and I'm sure if I worked for Boeing, I could probably take a few shortcuts. But in our case, I want the throttle to work as expected, and I don't want the doors to fall off while we're driving. I hope that makes sense. Anyway, before I install this stuff, I figured I'd give you folks a better look at all the key components. Now at this point, I'm sure it's hard to imagine how all this crap is going to solve our boost control problem, but things will become more clear as we move forward in the installation. The basic concept is the throttle cable will pass through this gizmo as the throttle cable moves during acceleration, and it will pull on this extension arm. Now, the extension arm has a cam on it, and when the arm is pulled far enough by the throttle cable, the cam will activate this limit switch. And in turn, that will close the boost vent valve, and the little diesel engine will get the boost it wants. The reason this ended up being so complex is it's fully adjustable, and at this point we really don't know when to trigger the boost valve, so adjustability has been engineered into this gizmo to prevent problems down the road. As I mentioned earlier, we'll be mounting this trigger system on this steel bracket. Now, as it turns out, we actually looked for an easier solution, like perhaps mounting the trigger switch directly on the injector pump, and, well, there's no space on the pump to mount the switch and still have easy access to it. Another thing to consider is, this may not be the best solution, and off camera, we're already engineering multiple solutions. If you stick around, later in this video I'll show you what we're currently calling Plan B. Yep, always have a Plan B. Actually, this simple diesel project has the potential to get very complex, but that all depends on the audience. Right now, we're fiddling around with low-tech solutions, but we do have a plan, and we're actively working on a computerized solution for both boost and fuel control. Theoretically, by adding a microcomputer, we can fully optimize this old-school mechanically injected diesel engine for better performance and potentially better fuel efficiency. Well, within reason. You see, we'll retain everything that makes this engine reliable as far as being able to run after Armageddon, and we would only enhance the fuel and boost control. So in the event of a total system failure, the engine would still run fine and we would only lose a little bit of performance and efficiency. So currently this car gets over 70 miles per US gallon and can accelerate up to 55 miles per hour in about 20 seconds. So in order to squeeze more performance from this engine, we're going to have to adjust the fuel rack for more fuel at full throttle. Unfortunately, because the way the governor works on this engine, that means we'll also get a lot more smoke out of the exhaust. And in order to make this car drivable in an urban environment, we're going to need to actively manage the fuel rack to prevent big clouds of smoke when the car accelerates. So here's a question to the audience. Should we continue pushing the limits of this setup and throw some technology at the engine, or is this project done? Now, in case you're wondering, my background is in electronics and writing code, so this would be fun for me, but I'm not sure the audience would be interested in what can be done with a bit of code and some hardware. So go ahead and write in the comments, yes, continue with the project and make the car go faster with technology, or no, Jimbo, the car's good enough. And I'll look forward to seeing what you folks have to say. Alright, well, let's take a better look at this gizmo. So rotating this part is how we fine-tune where the switch is triggered. And we'll put it here for right now. Let me go ahead and press down on the accelerator so you can see this in action. Well, there you go. One fully adjustable switch that's activated by the accelerator. Now all I have to do is wire the switch to the valve. Fast forward a minute and the switch is wired. Now in case you're wondering, the micro switch is rated for 10 amps, so we're good there. I reckon we're ready to take this car out for a road test, but before we do that, I want to see how much the car weighs, so we'll run it through the scales at the Farmers Co-op, and as a bonus, we're also going to weigh the normal Honda Insight. So my best guess is this car weighs about 1,500 pounds plus or minus 50 pounds. Let's see how close I am. And I'm way off. The diesel-powered contraption is tipping the scales at 1,660 pounds. Well, that's still very light in the grand scheme of things, but it's a lot heavier than I thought. Let's see how much a regular Insight weighs. Now, according to the internet, it should weigh close to about 1,800 pounds, or thereabouts. Well, this guy's weighing in at 1,840 pounds, and that seems about right. Okay, we're back in the Diesel Insight. Off camera, I went ahead and adjusted the switch so at a steady throttle at cruising speed of 55 miles per hour, the boost will be active. That works out to be a good compromise because we still get active boost on acceleration. I'm still having problems getting the second camera to work, and this time around I managed to get it to focus correctly, but now we have vibration issues, so we're only going to show the single camera view today. Now, unfortunately, you won't be able to see the boost gauge clearly. However, I did put an indicator light on the boost gauge, and whenever it lights up, we're getting full boost. Oh yeah, I also prepped the car for a fuel economy run, and well, I really don't care about the fuel economy per se, but I am interested in how much drag the supercharger is putting on the engine when cruising at 55 miles per hour. So perhaps the fuel economy data will tell us something. Another thing I'm interested in is the intake manifold air temperature. As I recall, the last time we took the car out, we were seeing rather high temps, and I believe they were in the range of about 160 degrees Fahrenheit, or a little bit more than that. Now on a gasoline engine, temperatures that high will definitely have an effect on performance. However, on a diesel, it's hard to say. Diesels seem to like intake temps between 90 and 100 degrees Fahrenheit. What that means is going below 90 isn't very beneficial. Now, some manufacturers like to display a warning when temps get above 160 degrees, and on some engines, they'll actually shut down at 170 degrees. I can guarantee we'll get above 170 today, and it will be interesting to see how much that affects performance and fuel economy. I'm sure a lot of you folks are yelling at your computer screen right now about perhaps installing an intercooler. Yep, we'll install one, but not today. Today, we'll make this engine suffer a little bit. It's all in the name of science. Now, I do read the comments, and some of you folks need to understand that the stuff that you read in textbooks is derived from doing experiments like this. Now, it's hard to filter through some of the comments, and I have to say over the past year and a half, I've gotten thousands of comments from folks who flat out said that none of the stuff I'm doing will actually work. Well, as it turns out, we've had a decent amount of success so far. Actually, a lot of the time, I'm very surprised at what this car can do, especially when it comes to fuel efficiency. You know, one of the major drawbacks of using this engine is the fact that the injector timing isn't variable like on a regular diesel engine that's used in automotive applications. You see, normally a diesel engine that's used in a car or a truck has some sort of mechanism to advance the injector timing when the engine speeds up, but that's not the case on this engine. The injector timing is fixed, and what that means is we actually lose some power and some efficiency when the engine speed increases. Now, to compensate for that, I did modify the injector timing a little bit when we had this engine in the Saturn last year. It seemed to help, but it's not a perfect solution. So it looks like the air temperature on today's trip is rather hot. The boost, well, it's holding steady at 10 psi, which is nice, and the exhaust gas temperatures are staying below 500. Now, from past experience, I've noticed that the cooler the exhaust gas temperatures are, the better we do with fuel economy. The power windows on this car do not work without some major intervention, and today the windows are up and the interior of this car is stifling hot. But the good news is, this car doesn't stink as bad as the Saturn did. So this car is pretty much just a YouTube car, and its only purpose is to do experiments on YouTube. Although I have occasionally driven it to the hardware store and a few other places in town. Overall, it's actually very easy to drive, and I have developed a certain amount of trust in it. You know, to the point where I'll actually drive this thing out in the middle of nowhere to do these fuel economy tests. The other Honda Insight that we have, well, let's call that the normal Insight for now. That car is very difficult to drive. I think I've put over 1,000 miles on that car already, and I'm just starting to figure out how to drive it. Now, unless you've ever driven one of those cars, you have no idea what's involved. You would think that because it's a Honda, it would be pretty much a normal car. Nope, not even close. There's actually a reason why they only made 16,000 of these cars, and for the most part, it's not a car for normal people, especially the 5-speed version. I have a lot of first-generation Insight owners in the audience, and I believe most of them would agree with me. Sure, the car gets fantastic gas mileage, but it takes a lot of effort, especially if you drive it the way I do, and I like to drive fast. Anyway, the difference between this diesel-powered contraption and a real Insight is night and day. This car, well, it's easy to drive, and the gear ratios on the Saturn MP3 transmission that we're using totally make sense, and this car just goes down the road without any issues. Yeah, it's loud and it's stinky, but that just adds to the charm. Fast forward 65 miles and we're back at the shop. It was certainly getting hot inside the car, and I'm glad the road test is over. Speaking about hot, the supercharger was pumping out a lot of hot air according to the thermocouple gauge, but everything under the hood seems only slightly warm, but not really hot. Yeah, for a 65-mile trip, you would think stuff would get real hot, but that's not the case. Okay, we have some data. Well, first of all, the car drove fine and it had plenty of power. Now, once getting the car up to speed, I was able to hold the throttle steady and I was able to maintain 55 miles per hour no problem. Now, a few times I did give it the beans and accelerated from 55 to 60, and the engine pulled strong. The exhaust gas temperature stayed between 420 and 475 while cruising, which is great. However, the intake manifold temperatures were way above 170, and most of the time it hovered near 180, although I did see it spike to 186 for a short period. So that's pretty high when you consider the outside ambient temperature was near 70 degrees Fahrenheit. So we do have a huge delta. I reckon the intake temps will only get hotter as the ambient temps go up here in Kansas. Now, despite the hotter than ideal intake temps and the added load of the supercharger continuously pushing out 10 psi of boost, the car managed to get 69.54 miles per US gallon. So yeah, we did see a decrease in fuel efficiency, but was that from the load of the supercharger or the hotter intake manifold temperatures? It's interesting either way. Now, our high water mark for fuel economy was 73.58, and that's when we were running 5 psi of boost, and the intake temps were ranging between 94 and 98 degrees Fahrenheit. I think the obvious next step is to install an intercooler to drop the intake manifold temps to something more reasonable. I figure in about a month or so, we'll be seeing ambient temps in the low to mid 90s, and that's likely going to cause a massive increase in temperatures at the manifold. Overall, the solenoid boost valve works, but realistically it should have at least 2 settings. Perhaps a 5 to 6 psi on the first stage and full boost on the second stage. Hey, let's have a look at Plan B. Overall, I think we're making decent progress, but this solenoid valve is very limited and basically is just an on-off for the boost. Perhaps we need to try something different. So this is a miniature throttle body from one of my fuel-injected small engines. This guy ended up in the junk pile because it's too small, but I think we can repurpose it as an analog boost dump valve. As you can see, we can vary the opening on this tiny throttle body, and something like this would give us better control of the boost. Of course, given the small size of the supercharger and the overall consumption of the engine, this analog dump valve would actually be too big, and we would only need to vary the opening a small bit. We could probably do that with cables or whatnot, but perhaps automating it with a servo would give us more flexibility. So, off camera I went ahead and designed and 3D printed the parts needed to make this servo controlled. Now all of these parts are just prototypes and they're printed in low temp PLA. I like to make prototypes in PLA plastic because it's cheap. However, PLA is not suitable for underhood temps, so the final design would be printed in ASA plastic. Let me go ahead and assemble this so you can get a better idea how all this stuff fits together. So just as a reminder, and I don't want to come across as snarky, this video series is about the trials and tribulations of installing a small supercharger on a small diesel engine. Our focus is entirely on a supercharged diesel engine because this is different than what everybody else is doing. Most of the people who watch this channel appreciate seeing the data we generate and the problem solving that we do. There's no other channel on YouTube that comes close to doing what we do, and that's what makes us different. By the way, consider subscribing if you haven't done so already. Okay, so for this tabletop demo, I'm going to be using a $7 servo test board. If we decide to go down this route, we would of course use something different to control the servo. I don't know, this probably isn't a simple solution, but I feel like it's going to be fun. Now of course we'll be using a microcomputer like an Arduino, and we're going to try something different as far as commanding when this valve should open and close. Well, first of all, we're going to use a throttle position sensor on the throttle cable to monitor where the throttle is at any given moment. Next, and this is the weird part, we're going to be using an accelerometer to detect when the car is at cruising speed. You see, once the car gets up to cruising speed, I believe we can start dumping boost. I reckon the combination of the throttle position sensor data and the accelerometer data should be enough to optimize how much boost we need at any given moment. Now, we may end up using a pressure sensor as well, but that may not be necessary. Anyway, this is some fun stuff to play with, at least for me, but I'm not sure you folks want to see stuff like this. Well, since we're on this topic, let's take a look at how we plan on controlling the fuel rack. This is the spare Kubota engine that we have, and it's identical to the engine that's in the car. It's an old school mechanical fuel injected diesel engine. Now, that's not too strange. However, we do have to consider that this engine has a mechanical governor controlling the throttle. That's where things get a bit difficult. Here, let me explain. So here's a cartoon of the accelerator in the Honda. Nothing weird here. The weird part is how the accelerator works with a mechanically governed engine. It's not the same as what you would expect on a regular car. So the engine that we're using has an idle speed of 1000 RPM and the RPM is capped at 4000. So the RPM range that we have to deal with spans a total of 3000 RPM. Now, the way the governor works on this engine is, pressing down on the accelerator about halfway will increase the engine speed from 1000 RPM to 2500 RPM. Now, it doesn't matter if there's a load on the engine or not. At half throttle, the engine speed will ramp up to 2500 RPM and stay there. You see, it's the job of the governor to hold the engine at any given speed that the throttle commands. If we add a load and it slows down the engine, well, the governor will automatically move the fuel rack a little bit to compensate for the load and bring the engine back up to 2500 RPM. For the most part, this quirk in the throttle is easy to get used to, and it's no big deal. The problem is when the throttle is initially pressed down halfway, well, the governor will actually quickly compensate and slam the fuel rack to its extreme limit for a few moments. Then, as the engine gets close to 2500 RPM, the governor will back off on the fuel rack and stabilize the throttle. So again, that's not a big deal, and it's hardly noticeable. But it is noticeable when you look at the tailpipe, because we get a larger than normal puff of black smoke from the exhaust system. A little puff is normal on a diesel engine, but because our engine has had the fuel rack adjusted way past its normal limit, we tend to roll a little coal when we initially accelerate. Now, there are two ways to fix this issue. First, we would have to adjust the fuel rack back to its calibrated position, and trust me, we don't want to do that. The second is we add more boost. You see, more boost not only makes more power, it also cleans up the exhaust. The problem is, with more boost, we still get a puff of smoke, but to a lesser degree. Now, none of this really matters where we test out in the boondocks. However, we eventually want to try driving this car in a city environment, and a Honda Insight rolling coal in downtown Wichita will attract the attention of the authorities. Now, we do have other options. We can actively adjust the limit position of the fuel rack. Now, this is nothing new, and it's been done for years on turbo diesel engines. As a matter of fact, my old turbo diesel Mercedes had something called an ALDA, and it did exactly this. Well, since the engine we're fooling around with ain't exactly a normal car engine, probably the easiest thing to do is to build an electromechanical device to modify the limit of the fuel rack. Here, let's have a look at what we're dealing with. So this is the fuel rack adjustment screw. In the past, I've used this diagram to illustrate how the screw is critical in adjusting the rack to deliver more fuel at full throttle. What we need to do is remove this screw and replace it with something that can be adjusted with either a servo or a stepper motor. Now, theoretically, we could attach a servo or a stepper motor directly to this screw and spin the screw in and out to adjust the rack position. That's a bit sketchy, and we won't be doing that. Instead, we'll replace this adjustment screw with a modified M3 bolt. This bolt has a 3mm hole drilled down its center, and that will allow us to insert a 3mm stainless steel rod through the bolt, so we can push the rod in and out quickly to alter the limit of the fuel rack. Now, keep in mind, this is just a demonstration of how the system will work. The parts I'm using are not necessarily the parts we'll actually use. On this spare engine, we have plenty of space to play in, but in reality, there is very limited amount of space when this engine's in the car. Okay, so now I can stick this rod through the hole, and I can actually push against the fuel rack to cause it to move. The next problem we need to solve is, we need a way to push this rod in and out, and that can be done many different ways. Now, one of the ways we're toying with is to use an Acme screw. You see, twisting this screw about half a rotation will give us all the movement we will actually need. The original limit screw had an adjustment range of less than 2mm, which is close to what this Acme screw can do in half a rotation. Now, we are going to look at other methods, but this one was easy to demonstrate on camera. No matter what design we come up with, it has to be precise, durable, fast-acting, and really small. We just don't have the space on this side of the engine, and to make matters worse, the alternator and water pump belt also occupy the same space. But no worries, when the time comes, I could probably whip something up in less than a day. Anyway, before I take this project to the next level, I need to know if this is something you folks want to see. And if you do, make sure you let me know in the comments. Writing a yes or a no is all you really need to do. Well, right now I need to get working on the intercooler, so you don't need to write anything about that in the comments. Anyway, we'll see you next time. Until then.